Great. So what I want to do to kick us off today is look at a few vector spaces. We're going to have these all be vector spaces over the real numbers, and it's significant that they're all over the same field. But let's make the first one 2 by 2 matrices. I'll make it explicit that this is over the real numbers. So these are just, what lives inside this vector space, things like A, B, C, D, where all entries are real valued. And another vector space we might think of, well, how about we think about P3? We talked about that a good bit. Again, over the real numbers. So things that live in here will be like whatever your coefficients are, constant coefficient, coefficient times x, coefficient times x squared, plus coefficient times x cubed, lives inside of P3. Let's do another one. How about something like, I don't know, just R4. So what lives in there? Well, here it's vectors. Here it's vectors like A, B, C, D, right? And you could come up with more vector spaces if you want, but here's a sampling of some of the vector spaces we've talked about. Now, what do all these vector spaces have in common? Well, yeah, okay. They're all vector spaces, and so they fulfill the axioms of vector spaces, that within them they have vectors v and vectors w, and you can add a vector v and a vector w and get another vector. You can add 2 matrices, get another matrix. You can add 2, 4 tuples, vectors with 4 values, and get another such vector. You can add 2 degree 3 polynomials and get another one. So that's certainly true. Good. These all happen to have dimension 4, right? So if we think about like the basis for these, this first guy has a basis of, well, several bases, but perhaps the most natural one is just this one, where we leave the values to be 0 and have a value of 1 in each of the 4 corners. What's a basis for this other guy? For these polynomials? 1x, x squared, x cubed, and a basis for R4 would just be, well, all the different places you can put 1. So 1 could be in the first value, 0 is everywhere else. 1 could be in the second position. 1 could be in the third position. And 1 could be in the fourth position. Okay. And because they all have bases with 4 elements, the dimension of these is 4. So these are all examples of dimension 4 vector spaces over the same field, over the reals. What I want to talk about today is the fact that, well, in some sense, these are all the same vector field. What do I mean by that? Well, first of all, let me clarify what I don't mean by that. Obviously, a set of matrices is not the same as a set of polynomials, right? So like in that sense, they're obviously different. A matrix is not a polynomial. So as a mathematical object, the set of matrices will be different than the set of polynomials, or polynomials of degree at most 3. So it's like, okay, there's certainly some ways in which they're different. And those differences are significant, right? Like, we can do things over here that we can't do over here. So what are some examples of things you can do to a matrix that you can't do to a polynomial? Yeah, you can ask what the determinant of it is. Oh, my mic came down. Getting a little bit of feedback, perhaps. Is that okay?
Yeah, as long as you don't have that touching it.
Oh, I can bring it down a little bit. Okay, great. So we can do things to matrices that we can't do to polynomials, such as you were saying, take a determinant of a matrix If someone asks you what a determinant of a polynomial is, you're like, I don't know what you're asking, right? You can find the trace of a matrix. You can do things in polynomials that you don't typically do to matrices, like calculate the degree of the polynomial, or calculate the, what else? What are some things you do to polynomials that you wouldn't do to a matrix? You can factor it, yeah. We will talk about matrix factorization in a few weeks here, but it'd be a very different kind of thing. You can plug in values for x, right? Like, that's a different kind of creature. And we can do things with vectors that we don't do up here, like, I don't know, the cross product of two vectors, right? So like, if we just, the different mathematical objects. And even some of the things that we can do that's the same in both of them, well, those things like don't carry over. So you might think there's like a really natural relationship between these matrices and these polynomials, where you can just identify, you know, like the first basis element with the first basis element, and so on. Each basis element with each basis element. So in that sense, you're like, there's a really natural correspondence between this matrix A, B, C, D, and the polynomial that's just like a plus bx plus cx squared plus dx cubed. It's like, yeah, in some sense, there's a very natural correlation, but like not everything's going to carry over. You know, like think over here. What happens if I do like 1 plus x times 1 plus x? Hope this example works out. Like, what does that come out to be? 1 plus 2x plus x squared. Whereas over here, like, what's the thing that corresponds to 1 plus x? What will the matrix be? 1, 1, 0, 0. Yeah? The 1 plus x becomes 1, 1, 0, 0. Times 1, 1, 0, 0. What does that give you? Row times column, 1. Row times column, 1. Row times column, 0, 0. Right? Look, this is not the matrix corresponding to 1 plus 2x plus x squared. Instead, would have been the matrix 1, 2, 1, 0. Rather, you just got back the same thing, right? So like this is kind of weird. Like what's going on here? Okay, so there are certainly senses in which this is not the same kind of object as this. They're not the same sets. The objects inside them are not the same. If you try and do a natural matching up, don't expect things on one side to carry over things on the other side, in general. But if we just think about these as vector spaces, they're a whole lot more than just vector spaces, right? There's a whole lot more structure. But if we think of them as just vector spaces, then we want to say, well, in terms of all the axioms of vector space and all the things we do with vector spaces, then they all act the same way, right? So like, what are the kinds of things we do with vector spaces? Well, you add vectors and you multiply by scalars. You take linear combinations of things, right? So in our axioms of vector spaces, we didn't have anything about multiplying two vectors, right? That's an extra thing that comes with the fact that these are matrices and these are polynomials, so you can multiply them. But in general, a vector space is just about adding vectors, multiplying by scalars, building up linear combinations of things. And here, if you just think about building linear combinations of things, then sure enough, like this guy is some linear combination of like the first basis element plus some, you know, second basis element, third basis element, fourth basis element. And exactly in the same way that this corresponding polynomial is just some linear combination of, well, it's pretty explicit here, a times the first basis element, b times the second, c times the third, and d times the fourth, right? And in general, it's like if you add two matrices, therefore it's going to correspond to adding the corresponding polynomials, Right, so in terms of addition, this works out. If you scalar by something, like if you scale multiply by 2, it'll correspond to the same thing as scale multiplying your polynomial by 2. So in terms of scaling and in terms of addition, these are, in some sense, they look and they act the exact same way. So let me make that precise by giving you a definition. First, I'll recall a previous definition. If we're given two vector spaces, let's emphasize that these are finite dimensional vector spaces. V and W, a linear transformation T from V to W is just some map satisfying two properties. T of V plus W is T of V plus, oh, I really don't like this notation V and W. Let me instead say V1 and V2. I like that a little bit better because these are both vectors beginning in V. Obviously it's equal to itself. Is T of V1 plus T of V2. And T of some scalar times V1 is that scalar times T of your first vector, where your V1 and V2 are in your vector space. And your C is just over your field. So we need these both to be over the same field in order to make sense of your scalar, right? You want your scalar to be some value in your field, so you can multiply it either before, you can multiply when you're in V, or you can multiply it after the linear transformation, you can multiply in W. We've already seen this. We understand linear transformations. But now I want to say that there's some sense in which, well, these all look the same. So what is that? What I mean by that? We're saying V and W look the same, or isomorphic. So that's just a nice Greek word. Iso means same, morph means shape, right? So to morph is to change your shape. Iso is just shape, same shape. So they have the same shape, they look the same. V and W isomorphic if T is invertible. So let's just think a little bit about our examples here. T from the set of 2 by 2 matrices to the collection of polynomials up to degree 3 can be defined by what it does to your basis vectors, right? Because once you define it on your basis vectors, you can extend it linearly over all of T. So it can be defined by T of your first basis vector, 1, 0, 0, 1, 1, 0, 0, 0 gives you out 1, and T of 0, 1, 0, 0 gives you out x, and T of 0, 0, 1, 0 is just going to give us x squared, and T of 0, 0, 0, 1 is giving you x cubed. So define it by this, and extend linearly. What do I mean by that? I just mean that in general, T of some A, B, C, D, since that is just A copies of the first guy, B copies of the second, C of the third, and D of the fourth, should come out exactly as we said it is, A copies of where the first guy gets sent, plus B copies of where the second, plus C copies of the third, plus D copies of the fourth. Right, so this is your linear transformation. And notice this is invertible. This has an inverse. Your T inverse is just a map from polynomials to M2 of R. And it's just defined in the obvious way. You just take 1 back here, x back, x squared back, and x cubed back, and extend it linearly. So it just takes any polynomial of this form to the corresponding matrix. Right? So in general, this just takes some polynomial, a plus bx plus cx squared plus dx cubed, right back to the matrix A, B, C, D. But what I want to stress is like any kind of vector space kind of stuff you could do in M2 will look exactly the same as in P3, right? So it's like, okay, you might want to take some matrix, I don't know, give me some example. I'll just throw some numbers in here. 2, 1, 3, minus 1, and add to it 2 times a copy of another matrix, minus 1, 0, 1, 3. And the point is, whatever you come out with here, let's just do it. 2 plus 2 copies of this is 0. 1 plus 2 copies of 0 is 1. 3 plus 2 copies of 1 is 5. Minus 1 plus 2 copies of 3 is 5. Will be the exact same as if we just looked at what happens with the corresponding polynomials if we apply t to it. It's like, why? Because t of this whole thing is exactly the same as, by linearity, t of 2, 1, 3, minus 1 plus 2 times t of minus 1, 1, 0, 3, which then just gives you out your corresponding polynomials. We could write these corresponding polynomials. This is just 2 plus x plus 3x squared minus x cubed plus 2 times minus 1 plus x squared plus 3x squared will come out to be exactly the same thing as whatever this polynomial corresponds to. X plus 5x squared plus x cubed. Okay, I think it's pretty much like beating this horse dead at this point. But like, is it clear what we're saying? We're saying like working in terms of, think of it just as a vector space in M2 is exactly the same, corresponds to working inside of P3. Right? Yeah.
Just a minor typo. Definition of a plus bx plus bx cubed plus bx.
Whoa! That's x, call me out faster. Yeah, that should be x squared and x to the third. Good. Okay, are we happy with this? Okay, so we're just saying isomorphics that look the same. Yeah.
This is the same thing. What's the difference between what's happening over there versus what's happening there?
Happening over here with what?
We just said that the 1, 1, 0, 0, 1, 0, 0.
Right, so this is multiplying the matrices. But when we talked about vector spaces, we didn't introduce any notion of multiplying vectors. Right, if you go back to axioms of vector spaces, all we had was adding vectors and multiplying by scalars. So I'm saying that if you just think of these just as vector spaces with the properties that vector spaces have, then they're going to act exactly the same way. If you realize there's actually additional structure that these objects have, well, they won't act the same way with respect to that additional structure. So isomorphism says they look the same in as much as you're just thinking of them to be vector spaces. Okay, cool. Yep.
Is it minus 1 plus x squared plus 3x cubed and x?
Okay, yeah, everything is wrong. That's an x cubed. That's a 5x cubed. So, you know, do as I mean and not as I say or whatever, right? Yeah, okay, good, good. Okay. So let's talk a little bit about what some properties of isomorphisms. Isomorphism is saying, in some sense, two things are the same. It turns out, in isomorphism between vector spaces is an equivalence relation. Have you guys seen equivalence relations in other classes before? It's like in math we have these different notions of what does it mean for two things to be the same. It's not quite that they're equal, right? I mean, they're not strictly equal, as in one is matrices and one is polynomials, right? Not exactly equal. But they are equivalent in the sense that they have these kinds of properties that equality has. In particular, we say it's, remember the properties of an equivalence relation? What are they? What are the three properties you have to satisfy to be an equivalence relation? Yeah, you have to be reflexive. You have to be symmetric. And how am I spelling this wrong? Reflexive? No, it's reflective. Surely we know how to spell. It's reflective. It's the reflective property, right? Okay, go on Google this and put it, tell me that it's wrong, whatever.
Reflexive. Yeah, it's reflexive.
With an X?
Yeah.
Look at that. Yes, that's right.
I see you flexing on me.
You typed it 355.
Should have slept last night. Okay, reflexive, symmetric, and the last one is transitive, right. And what that's saying is, in particular, any vector space should be isomorphic to itself. What is symmetric saying? If V is isomorphic to W, then W is isomorphic to V. And transitive, if V is isomorphic to W, and W is isomorphic to some third guy, which I guess I'll call like fancy X, almost like a chi, I've been trying to make it fancy, then your vector space V will be isomorphic to your vector space X. Right? So let's think about why each of these is true. So help me out with the first one. In order for it to be isomorphic, I need some invertible linear transformation from V to itself. What is that invertible linear transformation? Yeah, just the identity map. So, lots of ways you could write this. I guess I'll just write it like I of V is just the map from V to V that sends any vector V to itself. And obviously it's linear, right? And obviously it's invertible. It is its own inverse. Okay, symmetric. Suppose I begin with some map T from V to W, which is an invertible linear transformation. I need you to tell me what's an invertible linear transformation from W to V. Good. So you're noting that since T inverse is the inverse of T, T inverse itself has an inverse, which is T. Right? Like T inverse is invertible. Since T is invertible. Namely, what is T inverse inverse? Just t. Right. So that's how we get symmetry. How about the transitive property? Suppose I have some map T, some invertible linear transformation T from V to W, and I have some invertible linear transformation S from W to X. What is my invertible linear transformation from V to X? I want some map that's going to take me from V to X. What is that map?
That's composed to.
Good. You just put these together. It's like I first go from V to W, then from W to X. Since those are both invertible, the composition will be invertible. So let's make sure to do the order first. First I want to do T and then S. So S composed of T. And note for that bottom one, what is the inverse of this guy? This comes out to be, we gotta be careful. The inverse should be going from X to V. So first from X to W, then W to V. So it's going to be S inverse, T inverse composed. Right? Okay, so in some sense it's like equality. It's not saying the sets are equal. It's not saying that matrices are exactly the same thing as polynomials. No, no, no. But as vector spaces, they'll give us, all the same behaviors. So if you understand one vector space fully, like this guy, then you already fully understand this other one as well as vector spaces. Okay. Cool. Are we happy with that? So I started out by giving you a number of vector spaces. M2 at 2 by 2 matrices, P3, polynomials of degree up to 3, and R4. We notice they all have something in common. They're all degree 4. What do you think we can say about isomorphisms? What's a good way to tell if two vector spaces are isomorphic? It's a quick test. That would tell us if two finite dimensional vector spaces are isomorphic. Okay, and when's that going to happen? If you have two vector spaces, when are we going to be able to say, oh yeah, these are the same to each other as M2 and P3? Same dimension, right? Because then you just have to line up your basis elements, and then by linearity, you actually get all the properties follow that you want to follow, right? So how do we show that? Well, I'm first going to do as my first step, I'm just going to note that if you have some vector space V that is n-dimensional, okay. So why is this the case? Well, if V is n-dimensional, then V has some basis, V1, V2 through Vn. And what's a linear transformation? How are we going to define it? Right. We're just going to send V transformation. We're going to send each guy Vk to the corresponding coordinate vector of Vk in terms of the basis B, which will just correspond to the guy that's zeros all the way down and has a 1 in the kth position, right? So V1 will just get sent to 1, 0, 0, 0. V2 gets sent to 0, 2, 0, 0, 0, 1, 0, 0, 0, and so on. And then you can just extend that linearly, which exactly gives you the map, some guy, C1, V1, up through Cn Vn will just get sent to its coordinate vector, which is just C1 through Cn. And it's like, well, it's trivial that it's linear and that's invertible. It's like, done, right? This is pretty clear. But then, since being isomorphic is transitive, we can actually say something stronger. If V and W are finite dimensional vector spaces over F, well, V will be isomorphic to W exactly when the dimensions are equal. So let's prove this. We've already proven one direction. Which direction is that? Which way? Up or down? Up, right? So this up direction is just by a theorem and the transitive property. Right? Because if you have V and W and the dimensions are the same, say the dimensions are both, n or something, you get that then V will be isomorphic to Fn, but Fn is also isomorphic with W, and so by the transitive property, V and W are isomorphic to each other. So what we really need to focus our attention on is proving this downward direction. If two vector spaces are isomorphic to finite dimensional vector spaces, then they must have the same dimension. So let's suppose that V and W are isomorphic. How are we going to be able to say something about dimension? It's like, well, all we have to work with, this looks kind of ugly. All we have to work with, all that V and W are isomorphic. So let's just unpack the definition. Then there exists an invertible linear transformation T from V to W. And we want to be able to say something about the basis of V and the basis of W. In particular, that they're the same size. We don't know yet that they're the same size. So for as much as we know, we might have V, since it's finite dimensional, has some basis. We proved this a few lectures ago. That V has some basis, V1 through V, let's say M. And similarly, W has some basis, call it C, which is like W1 through Wn. But what I need to show is that my M and my N are equal to each other. Right? So the work cut out for us is to show M equals N. How can we do that? We have some invertible linear transformation between them. How do we know these have to be equal to each other? Yeah?
Express T in terms of the transformation between the two bases, and then look at the size of your T, because it has to be invertible. It has to be square then.
Oh. You're using the fact that, going back to a previous lecture, we can express our linear transformation as a matrix, the linear transformation is invertible exactly when the matrix is invertible, and therefore you're just forced to have m equal to n. So I guess we already have this result, right? But let me just give you a proof that comes directly from the definition of linear transformation, in case you're a little bit uncomfortable with the why can we express that as a matrix part. But yeah, we actually already have this. We've already done this. Because we can express this linear transformation as a matrix whose dimension will be n by m, right? And in order for a matrix to be invertible, it must be a square matrix. Very good. I'm instead going to argue a little bit more from a definition, which is that there exists this linear transformation. So then in particular, I'm going to say, well, let's do a proof of contradiction. Suppose that one of these guys is bigger than the other. And I want to make sure I suppose this correctly. Let's suppose m is bigger than n. Then we can think about what the linear transformation does to your vectors v1 through vm. You get a collection of vectors that's inside of w, and the dimension of w is n. So what does that tell you about these vectors if m is bigger than n? Yeah, you did a homework problem. So we talked about maybe this in lecture, but I think you also did a homework problem that if you have too many vectors more than the dimension, they must be linearly dependent. So then these vectors are linearly dependent. Thus, we can write some linear combination of the first one through some linear of the first one through the last one is 0 for non-trivial C1 through Cn. There's some non-trivial solution to this, right? So it means for them to be linearly independent. There should be m. There's m of these. There's m of these. And what are we going to do now? Well, let's use the fact that we said T is a invertible linear transformation. Since it's a linear transformation, we can rewrite this by pulling out this T. It's just T times C1 V1 through Cm Vm gives us 0. And then what can we do? Well, it's not just a linear transformation, it's an invertible linear transformation. So we can move T over as its inverse. So we get C1 V1 up through Cm Vm is equal to whatever this invertible, the inverse, T inverse does to the 0 vector. What does a linear transformation do to the 0 vector? A little proposition here, a little reminder. What is S of 0 equal to for any linear transformation S? What is it?
0.
Huh?
0.
Why? Proof. Why is that? Why does the linear transformation always send 0 to itself?
Multiply by a constant inside with S, like the 0 inside it should be equal to the constant times whatever it is. So.
Okay, so you're saying that S of some constant times a vector is equal to that constant times a vector, right? That's what it means to be a linear transformation. And now you're going to make that constant equal to?
Well, the vector is 0, and constant times the 0 vector is itself. So then whatever whatever S of 0 is, it has to be such that any constant times it must be the That's V itself.
Well, I was just going to say, just pick your constant to be 0. What's 0 times the vector, or the 0 vector? And then what's 0 times the transformation of V? Well, wherever this goes gets times by 0, so you get 0. Right? So that's one way to see it. I think you'll give it another way. Lots of proofs. You can, like this follows from lots of the properties, lots of the axioms of vector spaces. But in particular, since T inverse is also a linear transformation, we get out the 0 vector. So we have that there's some non-trivial linear combination of V1 through Vm that gives you 0. But wait, we said that V1 through Vm is a basis for V, hence they should be linearly independent, so this gives you a contradiction. Now we've only done the case that m is larger than n. You might still say, well, how about the case where m is smaller than n? Don't we have to rule that out also? But if m were smaller than n, then that's the same as saying n is larger than m. And v being isomorphic to w is saying that w is isomorphic to v. So now you still have w being mapped to v, where w has larger dimension. So actually, by symmetry, this is the exact same argument as this one below. So you only have to consider one case, and then you can be like, well, we can just think about the map going the other direction, and you have the exact same argument. Hence, we can conclude you must have m equal to n. Hence, we must have m equal to n. Okay. I guess we had already seen this before, just by thinking about the matrix corresponding to linear transformation, but I think it's kind of nice just to go back to and see the argument in terms of a definition of, this argument makes really explicit why we need this to be an invertible linear transformation, right? We use those properties in the proof. We needed both it to be a linear transformation and for it to be invertible. And now it's beginning to make sense where I define isomorphism as two vector spaces that are related by an invertible linear transformation. Okay, so in terms of vector spaces, you should think there's just one vector space over a field for any dimension. But this over R, or this over F part is like really, really significant, right? You had a homework problem about this when you thought about like Cn, and recall thinking of Cn over R is a rather different creature than thinking about Cn over C. The dimension of this guy, the dimension of Cn, and maybe I'll just put down here the ground field R, is, you showed it was 2n, whereas here the dimension of Cn over the ground field of C came out to be n. And so it's like the ground field plays a really significant role, right? So you might be like, well, can you think of like is C isomorphic to R2? It's like, it depends. If you're thinking of C over the real numbers as the ground field, and I assume you're thinking of R2 as being over the real numbers, then the answer is yes. They're both dimension 2. And so the answer is yes. Where, C, like how do you think about C? Well, elements in C are of the form A plus BI. So your basis here would just be the basis 1 and I. Where your scalars, your A and your B, are real numbers, corresponding then over here in R2 to having vectors A and B. right? So here your basis is just the basis 1, 0, and 0, 1. So like, think of them both as over the real numbers, then yes. But if instead you thought about C as being over the complex numbers, it's like, well, now what's your basis? What is your basis for C over the complex numbers? It's just 1. Because you allow your scalars to now be complex numbers, right? And that is not going to act the same way as R2. You have only one basis element, and you multiply by any complex number to get whatever complex number you want. So keeping in mind what ground field you're over, it's really important. Where are your scalars coming from? Okay, we'll stop there today.